We're going to derive the moment of inertia of a uniform disk of mass m and radius r, rotating about its center. So this would be like a view from above, and the disk would, say, rotate around an axis that's perpendicular to the disk and through the center. If you happen to be in my class, this is on page 271 in our notes. So what's helpful for getting started is, if you remember with moment of inertia, if you have a bunch of discrete objects, what you're doing is you're adding up the sum of each little chunk of mass times its distance away from the axis squared. Okay, so this is be for discrete objects. Okay, well this isn't a set of little point masses or discrete objects. It's an object where the mass is kind of all smeared out or distributed uniformly. Okay, and so what we need to do, instead of summing up a finite number of discrete masses, instead what we're doing is an infinite sum of little chunks of mass that we're going to call dm. And then we're taking that little chunk of mass times its distance away from the center squared. Okay, so this combination of dm times r squared, what that would be is that would be the moment of inertia of only like this little chunk of the mass, one tiny itty bitty bit of it, about the center. So if just this little piece was going round and round, that would be its moment of inertia. But what we of course have to do is add up all the pieces in the disk. So that's kind of the mechanism of what this integral actually does. So the challenge is usually to write what this little mass is. We need to know how much, what this thing weighs. What's its mass of this little chunk? Okay, so the way to go about this is it's a 2D object, so you kind of do it with kind of like unit conversion. So dm, it's a little chunk of mass, and what that's going to be is like mass per area times area, right? So it's the mass per area of this thing. Well, if it's a uniform disk, we kind of know that, okay? The mass, the total mass is m, and the total area is pi times like big R squared. So this full-on radius, typically the physicists call it big R, and then like little r would be like a little wiggly coordinate. As a matter of fact, I'm even going to put that in there. So there's like a little r and big R. And then the area of this thing, well, it's just a tiny little patch, so it's called dA. It's a itty bitty patch of this thing, okay? Well, so what we can do is to get the area of this itty bitty patch, this little, in fact, I'm going to write down dA. So dA is the area of this little patch. All right, but we have to work on this. We have to work on how big really is that area. How do we write that? And so what we need to do to get the area of this thing is we need to know how big is one side and how big is the other, and then we can kind of multiply them together. Well, this side's not too tough because you can see that's just a little excursion in R. So that is just going to be d little r. That's a little wiggle in R. And then here you're wiggling theta. Now a mistake people will make is, so I'm actually going to label this in the drawing. This is d little r. Now a mistake people will make on this one is they'll say, oh, I'm wiggling theta, so they'll write d theta. But d theta is not a length. That's a wiggle in angle. You have to multiply that wiggle in theta by like the lever that you're sweeping. So it's like arc length. Instead of r theta, it's going to be r d theta. So the size of this thing is r d theta. So you can see the area of this patch is going to be dr times r d theta. Now, for style, just to make it pretty, people will typically put the variables, the like variables, kind of get together. So they'll write it like this, r d theta. So that's your dA, right? And so what we can do then is put this in. So you have m over pi r squared. That's really just a bunch of constants. And then your dA is this r d theta. Okay, so that is a little chunk of the mass. That's how much this little piece weighs. And then what you'd have to do is multiply that thing by r squared and integrate. So then we can just shove this thing back in here. Okay, so we've got integral. Well, you can see we're integrating over two variables. So integral, double integral, we'll put the limits on in a second. Your dm is all this junk. So it's big M over pi big R squared. Okay, now notice you have r d theta, But then you're gonna have to multiply again by r squared. I tell you what, I'll go slow and write 2 lines of algebra. So first I'm gonna put this dm in here. So r d theta. But then you gotta multiply by r squared, okay? We'll collect this together. I just didn't want to go too fast with the transferring things over. And so then what we want to do is the r coordinate is going to start from 0, and then we need to go all the way out. So that's your, that's little r goes from 0 to big R. And then your theta is going to go from 0 to 2 pi if you want to go all the way around. Okay? And so then just to wrap this up, so that kind of sets it up. Let's get a bunch of constants out in front and make this a little easier on us. So m over pi big R squared, those are just constants. So pull them out, m over pi big R squared. Okay, times, now we've got, well, let's get everybody together here. So we've got integral from 0 to 2 pi. Theta goes from 0 to 2 pi. Integral from 0 to r of r cubed dr d theta. Okay. Well, the limits don't depend on the coordinates in this case, but what we'll do is, just for good habits, we'll work kind of inside out. So you have integral of r cubed dr, so don't worry about all this stuff for the moment. That's going to integrate to r to the 4th over 4. And then when you plug in, you're going to get big R to the 4th over 4. So that's just going to pull out big R to the 4th over 4, right, by the time you integrate that. So I'm going to pull that out front. We got big R to the 4th over 4. Still got this constant, m over pi big R squared. And then all that's left is this little integral over d theta, 0 to 2 pi d theta. Right? Well, d theta just integrates to theta, right? The integral of 1 d theta, the function that you would take the derivative with respect to theta to in order to get 1 is just theta. So this will just go to theta, and then you have to substitute 0 and 2 pi. So you get 2 pi minus 0 here. So this integral over d theta is just going to be 2 pi. So finally, maybe I'll show one more line here. So you have r to the 4th over 4, m over pi r squared, big R squared, and then this just integrates to 2 pi, the integral over theta. And then finally, let's get this. So r to the 4th will become a 2, and that r squared goes away. The pi's go away. And 2 over 4 makes 1/2. So you get 1/2 m times big R squared. Okay, so that is the moment of inertia of a disk about its center. I encourage you to get in the habit of, when you're working on this stuff, to check that your units, when you're calculating a moment of inertia, that you always get a mass times a distance squared. But that's the moment of inertia of a disk about the center.